Hello and welcome back. Recall last video, we introduced the last of Newton's laws that we're going to be looking at this semester. These four laws quantify all of the motion that we can see in the universe with the detectors built into our head, which are our eyes. And just briefly going over them once again, the first law is known as the law of inertia and describes to us how objects will behave if there are no unbalanced forces acting on the object. So you add all of the forces that are acting on the object together vectorially, because forces are vectors, and you end up getting zero, then that means that the object is being pulled in all directions uniformly, and it will remain in a state of constant velocity or equilibrium. His second law tells us how objects will behave if we add all the forces up and don't get zero. Notice that if this numerator is not zero, then the object will experience an acceleration that's directly proportional to the magnitude of the unbalanced force in the same direction as the unbalanced force and scale inversely as the object's mass. It will experience an acceleration if it has an unbalanced force acting on it. The third law, forces come in pairs. You cannot have an isolated force. To identify the third law pair, you just simply switch the nouns in the direction. The fourth law, which it's not really known as the fourth law, is the universal law of gravitation. So notice I put fourth in parentheses. These are the four laws. It's not known as the fourth law. It's known as the universal law of gravitation. And remember that the magnitude part of the universal law of gravitation is the universal constant g. Product of the masses involved divided by the distance between their centers of mass squared. And then recall that the direction part of this force will always adhere to the fact that the gravitational field is attractive. In this video, what we want to do now is look and see why is it that the Earth dictates all gravitational interactions on the surface of the Earth. I mean, I'm pulling on everything in this room and everything in this room is pulling on me. Yet I am not moving toward those things and those things aren't moving toward me. I'm being stuck to the floor. I mean, I'm being pulled primarily I'm being pulled in several directions, but the largest pull is coming gravitationally from the Earth. And why is that is the question. So what I've drawn here is a circle which represents the Earth. And then I've drawn me here up at the top. So here I am, and here is the Earth. Okay, so give me a couple of hairs and a smile. There we go. Okay, so if I apply the universal law of gravitation to me and the Earth, then I would look at the force of gravity's magnitude between me and the Earth. This is the force that I pull on the Earth with and that the Earth pulls on me with as big G. Product of the masses involved. So what masses are involved? Well, this is the Earth's mass. And then this is going to be my mass, divided by the distance between our centers of mass. Where is the center of mass of the Earth? Well, the center of mass of the Earth is in the center of the Earth, and my center of mass is at my belly button. And so this distance r happens to be the radius of the Earth. So the distance between the center of mass of the Earth and my center of mass, if I'm on the surface of the Earth, is the radius of the Earth. So this is divided by the radius of the Earth squared. That's the magnitude part. What direction is the Earth pulling on me? Well, remember, all gravitational interactions are attractive. So when I'm talking about the force that the Earth is exerting on me, the Earth is pulling me toward its center. So you can see that the force is directed along the line that connects me to the Earth and directed toward the center of the Earth. I also pull on the Earth, but I pull also along the line that connects me and the Earth, but I pull up. I pull toward me. I'm pulling the Earth toward me. So both of those forces lie on this line, but in opposite directions. Notice here that if instead I wanted to find the force of gravity on you, so let's say this is you, So I want to know what is the Earth's gravitational force being exerted on you. Then this is going to be big G. The product of the masses involved. So this is the force exerted on you by the Earth. So this is going to be the mass of the Earth and the mass of you, divided by, again, it's that same distance, which is the radius of the Earth squared. So the distance between your center and the Earth's center, again, is still the radius of the Earth. And actually, it doesn't matter what object we're considering near the surface of the Earth. If we're trying to find the Earth's pull on that object, notice that these quantities right here are going to be the same for all objects on the surface of the Earth's interaction with the Earth's gravitational field. Those are all going to be the same. So that collection of constants, let's look at it a little bit more closely. So we've got big G, the mass of the Earth, divided by the radius of the Earth squared. What is this number? Let's just look in the front of the book and see what values. You can do a Google search and see what we can plug in as far as these values, what they're equal to, and what this number ends up being, and the units. Okay, so remember that big G is 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. The mass of the Earth is 5.98 times 10 to the 24th kilograms. And then we're going to divide that by the radius of the Earth, which is 6.38 times 10 to the 6th meters. And we got to square that whole denominator. Be careful. When people are calculating this number, it's very common that they don't use parentheses in the denominator and then square it. So be real careful how you enter this into your calculator. So let's go ahead and grab our calculator and put these numbers in and see what pops out with this collection of constants, which again is the same for every single object interacting with the Earth's gravitational field on the surface of the Earth. So what we come up with is 9.80. And what units do we come up with? Well, we've got meters squared here and meters squared here. So these meters squared and this meter squared are going to cancel. Kilogram here, those kilograms will also cancel. And what are we left with as far as units go? Whoops, that should be kilograms squared, sorry. Big G is Newton meters squared per kilogram squared, sorry. So I've added the little squared there. We get rid of just 1 unit of kilogram. We still have 1 unit of kilogram here. And so we end up with a Newton per kilogram. And what is a Newton per kilogram? Well, a Newton is a kilogram meter per second squared divided by a kilogram. Kilograms will cancel. And so this number is 9.80 meters per second squared, which I hope you identify as little g. So it turns out that this collection of constants we give a special symbol to, because this collection will be the same for the Earth's gravitational pull on any object on the surface of the Earth. So instead of memorizing what big G is, what the mass of the Earth is, and what the radius of the Earth is, instead we combine all of those constants together and we just assign the number and the units a special symbol, little g. Now notice that if instead we're on the moon and we want to know what the gravitational pull on us is by the moon, then little g would have a different value, and that different value would be big G, 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared, times the mass of the moon divided by the radius of the moon squared. So this would be a different value. G would have a different value on the moon. Same with Mars, same with Venus, any entity at all. So up till now, what we've been doing is saying that the force of gravity exerted by the Earth is equal to an object's mass times the acceleration due to Earth's gravity. And now you see why this is true. Notice that this collection right here can be replaced by little g. So when I talk about the gravitational force on me, it's little g times my mass. When I'm talking about the gravitational force being exerted on you, it's little g times your mass. And that extends to any object on the surface of the Earth of which I want to find the Earth's pull on. Always little g will be the collection of constants times whatever the object's mass is. So you can see that this is what we've been using all along, and you can see now where it comes from now that you know Newton's universal law of gravitation. So now coming back to why is it that the Earth is dictating the gravitational interactions for objects near the surface of the Earth. So remember, I'm gravitationally attracted to you too. I'm also gravitationally attracted to all other bodies in the universe, all objects on the surface of the Earth. Everything is pulling on me that has mass, and I'm pulling on everything else. Yet the main interaction is being dictated by the Earth. And you can see when you look at these quantities, this big G is involved in all interactions, so it's going to be the same number regardless if I'm looking at my gravitational interaction with this pan or with the Earth. This big G will remain the same. But check out this mass of the Earth. This is a huge number. This is basically 6 with 24 zeros after it. Okay? The mass of this pan is teeny in comparison. Now the distance between me and this pen is very small, right? So I would have a small number here, okay? But only maybe 10 to the, a little bit less than 10 to the 1. Notice that this 10 to the 24 is way overshadowing a difference in this distance, 6 times 10 to the 6th. Even squared, this is going to give me 10 to the 12th. Okay, so this is with 12 zeros behind it. So this mass of the Earth dictates the gravitational actions that happen near the surface of the Earth. Now as an object, it's further and further and further and further away from the center of the Earth. So, you know, a rocket that's taking off from the surface of the Earth and is traveling far and far away, as it's further and further it goes, the weaker and weaker the Earth's gravitational pull on it is. It never reaches zero because there's always a distance between the object and the Earth that we can plug in for our value for r. But you can see the further and further away two objects get from one another, the smaller the gravitational force. So as objects get far away from the surface of the Earth no longer dictates the gravitational interactions. But here at the surface of the Earth definitely does dictate the interactions. The other thing I'd like to say as far as the universal law of gravitation goes, is that this form of an equation is known as an inverse square law. So this is known as an inverse square law. Okay? Why is that? Well, it's because the magnitude of the force cares about the inverse square of the distance. So the further and further away we get, the force being exerted on the object by another, the further and further two objects get from one another, the force being exerted by each on the other is falling off as 1 on r squared. And this has a very distinctive curve associated with it, these inverse square laws. So if we look at force versus distance, we have these very characteristic curves, these 1 on x squared, where x is r in this case, 1 on r squared curves, that are very large and actually infinite at r equals 0, and then drop off and approach 0 as r gets really large, but never actually reach 0. So now we see where mg comes from. Now we see why the Earth's gravitational force dictates all gravitational interactions. And next video, I think we will work with some problems in the gravitational field. So we'll see you next time.